But we might want to do better than this, because this only really works at these horizons. So it's a lot harder to calculate a full spectrum if you are just at an arbitrary position. And so instead, we have implemented a framework that was developed in the last decade or so to calculate an effective Hawking temperature. And I don't want to go through the details too much, but the basic idea is that you have boundary conditions at the past, and you could treat these as an emitter, somebody who's emitting a signal that reaches an observer, which is just falling into a black hole. And the ratio of the frequency detected by the observer to that sent by the emitter will tell you information about the effective temperature. And in the limit that the temperature is sufficiently adiabatic, there's this specific condition, then this reproduces the exact Hawking effect that we expect at infinity. So with this framework, it's nice. It doesn't really require much numerical work. It can be done entirely analytically, and you get this result. So for a Kerr black hole, in general, the temperature, let's look at this plot right here. We can see that as R goes to infinity, the temperature, the red one, tends to go to a constant value. This is the normal Hawking temperature at infinity. But as you fall into the black hole, that temperature increases ever so slightly before then decreasing. The dashed lines are negative because we're on a log plot. And so it continues to decrease until it reaches negative infinity at this point, which is the inner horizon. So I'm just focusing on the red one for now. So this is the radiation that you would see if you're looking downward directly at the black hole. But you can also do the same thing for the radiation seen from the sky above you. Hawking didn't really have that because he was considering observers at infinity. But in general, your space-time around you in every direction is curved and should produce some sort of particles from that quantum field. And so we can calculate it. Now we can go one step farther here. So we've said that the amount of Hawking radiation diverges at the inner horizon. So what about the inflationary Kasner solution? Oh, and I guess I should say it diverges as 1 over the horizon separation distance. So if I include the inflationary Kasner, then it might look like this. So again, we have our 2 stages, inflation and then collapse. And we can see that the temperature turns around again, but then eventually diverges to positive infinity once you reach the space-like singularity in the inflationary Kasner model. So this is the general picture that we have. Hawking radiation diverges, at least in the radial direction, once you reach the inner horizon. And this is in the absence of any accretion. So even if your space-time is completely empty, your black hole is completely isolated, even the mere presence of a quantum field that is initially empty in a vacuum state will cause particles to be created that are going to diverge at the inner horizon. So we should expect that inner horizons probably don't form then, because you're going to have this wall of infinite energy that is created. Okay, so just a few more things. I want to go beyond just this radial temperature, because it turns out you can do this in any direction you look in the sky. So for Kerr, the general result is that for a 0 angular momentum observer, then the effective temperature diverges in every direction you look in your field of view. But this is observer dependent. So Hawking radiation is an observer dependent phenomenon. And so for a different class of observers, it only diverges along these radial directions that you can see in this plot on the left, that it goes to positive infinity behind you and negative infinity in front of you, or that actually might be switched. But the general idea is that you have these points of light that you can see with infinite temperature, but then everywhere else is relatively normal by comparison. But what I've shown in this work is that as you are going inwards, starting out at the event horizon and then climbing toward the inner horizon, that if you look in, say, 3 different directions given by these 3 curves, that there always will be at least one direction you look where the temperature does diverge. And so this instability does happen in just about any model that you throw at it. Okay, so I could show you more plots, but I figure the best way to do this would be with another simulation. So let's actually see what this looks like then. So same sort of thing as before. We're going to fall into the black hole, see what happens when we come out the other side. Except for now, I'm going to turn on Hawking radiation. So the first thing that we can notice is that there's this limb brightening effect. The Hawking temperature increases generally as you approach the edge of the black hole shadow and is the smallest at the center. My apologies in advance. There's a lot of numerical work that goes into this, so it's kind of choppy, but you'll notice that eventually the inside becomes negative temperature. It's kind of hard to show exactly what that looks like, but I've colored that blue. And eventually that grows to take over the whole black hole shadow. And as you keep going, that just keeps getting brighter and brighter over time and more uniform until eventually it diverges at the horizon. And beyond that, we get this wormhole that we now know can't actually happen because we've reached this infinite wall of energy at the inner horizon. Then we bounce backward. We can see we're escaping the white hole now. The redshifted universe is behind us. Okay, so this is the general picture. The conclusion of the matter is that Hawking radiation diverges at the inner horizon. And this happens for this case, which was the Reisner-Nordstrom black hole, but it also happens for rotating black holes and in the inflationary Kasner model as well. So just one more thing I want to point out is that you can do this with other black hole models if you'd like. So two projects that I've been focused on. One of them is with non-singular cores. So during my PhD, there was a work that came out where people proposed a type of black hole that managed to avoid the classical mass inflation instability. So they made this inner horizon an inflection point in the horizon function. And so instead of diverging at r equals 0, the horizon function remains finite. And this is a nice potential solution, because that would mean we don't have to deal with singularities and higher order quantum gravity. We can do everything with semiclassical physics. But what I found is that it doesn't really work out. And this was additionally propped up by Roy Kerr himself recently published a paper questioning the concept of singularities in the first place and claiming that his own solution provided a counterexample to the singularity theorem. And I don't want to get too much into that, but the basic idea is that a lot of people in the field want black holes not to have singularities. They want to have some regular core in them so that everything behaves nicely. But what I found is that Hawking radiation, even in this model, diverges. And no matter what model that you throw at it, semiclassically always acts to restore sanity or destroy your hopes and dreams if you want wormholes. And then the second project that I've been working on with student Dave Yanni, who's in the room here, is to work with models with cosmological constants. So anti-de Sitter and de Sitter black holes are of interest because when you reach that inner horizon, you actually are seeing the end of the universe. But in our real universe, it's not asymptotically flat. It is expanding over time. And so we might expect that to make a difference. And so we've been looking at what the Hawking radiation looks like in these sorts of models. Okay, so we've reached the end. Here is the summary of the semiclassical part of what we've learned, which is that the Kerr metric is not semiclassically self-consistent. If you are using the Kerr metric for calculations, then you should know that this inner horizon actually gets replaced with something else. But what we found is that there is a globally self-consistent model that semiclassically predicts that you will end up seeing a singularity here, because just about everything that we would calculate, vacuum polarization, the energy of the quantum field, Hawking radiation, it all diverges and produces a space-like singularity at the inner horizon. Now, you might ask, what happens after this collapse regime? So just like if you take a string and you decrease its length to 0, we know that decreasing length of the string increases its pitch. If you put your finger on a fretboard, then the frequency increases. But we also know that would imply that if you decrease the length to 0, you would get an infinite pitch, infinite energy. Of course, this isn't actually a problem, because if you take that limit L to 0, then strings don't behave like strings anymore. They behave like individual molecules which move around, and so we need new physics to describe that. And in the same way, we need new physics to describe this. And so I'll revert any questions related to that to you can ask Andrew in a few years what his string theory predicts. That's a good question. Yeah, you're asking about what negative temperature really means. And I do get asked that a lot because I think it means a lot of different things for a lot of different people. And we have to be clear what exactly we're talking about here. So for a lot of people, astronomers included, negative temperature means you have some sort of population inversion in your system. So you have a case where the excited state is more populated than the ground state. And so you can define that as just a negative temperature that gives rise to these OH megamasers and things like that. That probably is not what we're talking about here, because really, when I was referring to negative temperature, it was related to this black body spectrum. And so if you just plug in a negative temperature to that, then you find that means it's an ultraviolet divergent spectrum. And when we did the actual numerical calculation, then we showed that it isn't actually ultraviolet divergent, but it does sort of follow that shape for most of it. So really, I would think of negative temperature just as a really high energy version of temperature. So things are blue shifted. You could also think in terms of, so we think of Hawking radiation as spaghettifying tidal forces, which are pulling apart particles at the event horizon. In this framework, you can imagine that at the inner horizon, those forces are pancakeifying. And so that gives rise to this opposite sign that the particles still exist, are still created, even though the tidal forces are acting in the opposite direction. Yeah, so the white hole is the thing that we see right here, and I guess you could put it right here as well. The reason I'm including it is because the math predicts that's something that you can do with the equations of general relativity, and it looks cool. But what we've seen is that when you pass this inner horizon, everything beyond that is just impossible. So even though it looks cool and it might be nice to have wormholes and white holes, I think in reality, the conclusion is they don't actually happen. Yep. Yep, yeah. So you're mentioning gravity is renormalizable. And so if I go back to that slide, yeah, that is a perfect question. Because it's part of the reason why people say that gravity is incompatible with quantum mechanics is because if you try to do this renormalization process, you end up at each higher order, you need more and more renormalization constants that go to more and more higher orders. And so it's just an infinite chain of regress that never ends. And so you can't actually renormalize it to create an ultraviolet complete theory. But you can use it, and that's the thing that people have been working on through these past decades, is to find a way to find a complete effective field theory that's valid up to some energy scale. And so for us, this energy scale is above the unification of the standard model. And so any physics that we're used to in this universe happens in this one loop semiclassical limit. So yeah, great question. So why does the Hawking radiation make it so that wormholes can't exist? I guess it's essentially the idea that Hawking radiation is just a matter or radiation which is produced from a quantum field, which is initially in a vacuum state, but just particles get spontaneously produced. Those particles have gravity of their own, and that gravity pulls things inward. Usually that's negligible when people are doing simulations. You just ignored self-gravity from accreted matter. But once they get close enough to the inner horizon, then they diverge in energy, and so does their gravity. And so essentially, if you are trying to cross the inner horizon, even just one particle which is produced spontaneously is just going to suck you in and crush you into a singularity. So that is the idea, is that this infinite divergence causes the space-time to back react and collapse. Yeah.